happens when you like something a little more than you should and don't look at it dispassionately. That's the point. So talking about something dispassionate, 7 deadly sins. I don't think there are only 7. I think you can add a few zeros to that thing, and it'll still be true. But what we want to talk about was, what do we think, what do we see in people making common mistakes? And some of these mistakes are not things that people actually think about while writing code. In fact, quite often we don't think about them while writing code.
We're as guilty as any.
We find them after the fact, right? And if you look at DPDK's I/O pipeline, just the base I/O pipeline, whenever you see something that says I got 2x better in performance, means somebody didn't do their stuff right the first time. Now, we thought back in 2012 we had an absolutely brilliant fastpath that could bring in packets at a very, very fast clip. It was doing 29 million to a core. And then we found a way to do 34 million to a core. And then we found a way to do 40 million to a core. And then we found a way to do 60 million to a core, right? But all that comes out of basically mistakes we made. And I kid you not, there are still mistakes in the code which can allow it to go faster. But it's diminishing returns to some extent. But that's what we will try to talk about, okay? So the core of everything is this, the CPU core. I hope you guys can see it. This is, and so by the way, just one thing. Everything in this is essentially in one document. If you read that document inside and out, I guarantee you will sleep well for a long time. Okay, but there are typical sections in that document that are actually very interesting. It's officially known as the IA64 and IA32 architecture optimization guide. And it has the most interesting sections for us when we want to do high-speed programming is the section that deals with compilers and the hints Intel tells compilers to build. And all of that is what that guide actually contains. So if you go through it, and there are huge sections, it essentially is a guide of telling you what to do, what not to do. And then there's a few other things that people don't really think about, which we will try to talk about in this thing. But if you look at the basic execution code, and this is true of any execution core in the industry today, any one Neumann machine architecture essentially is a 5-stage, sometimes broken up into multiple stage pipeline. It's instruction fetch, instruction decode, data fetch, execute, store. And that's what that basically represents. So if you look at it, instruction cache, pre-decode, instruction queue is the basic front end. The instruction decode goes into a data fetch. That's what your prefetchers, data caches do. The next stage is the execute. We have somewhere between 5, 7, 8 ports of execute, depending on which processor architecture you go with. The execute at the end will issue a data retirement stage, which is the last end of the pipeline, and then the instruction goes off. But if you look at any processor architecture, it's that basic fundamental thing. Now, I know people want to talk about different processor architectures. They all map essentially to the same thing. We've done most of these architectures at some point in life. If you look at a 486 to a Pentium to a Pentium 2 to a Pentium 3 to today to an Atom, that spans a lot of the processor architectures, right? But all of them execute essentially off of a certain set of rules. And those rules are actually quite straightforward, okay? Yeah, anything to add?
No?
Okay.
Well, go ahead and move on. Yep.
Yeah.
So, okay, cop quiz here. What's the first part of the pipeline we need to start worrying about? Where should we start off? Any suggestions? What's before the fetch?
Actually, it's an interesting question because you have to think about what's before the fetch, before you fetch it.
Okay. The block that we need to consider before we even get the fetch is this one. You need to know where to fetch, and that comes into your branch prediction unit. Okay? Because before you even go to fetch the instruction, you need to go out to memory, or hopefully cache, and actually pull in the instruction as part of the fetch. So you need that address. So we need to consider the branch prediction unit, okay? And we need to make sure our code doesn't get branch prediction misses. I'm sure we're all pretty much aware of the fact that this is a large penalty. You've got to flush all your pipeline, and then you've got to refetch new instructions. You've got to throw away all the work you've done. However, on the other hand, it's not true to say that all branches are bad. Okay? You've got predictable branches, and you've got unpredictable branches. And your predictable branches are generally pretty okay. Yeah, they use a cycle. They are an instruction to execute. But as long as you predict correctly, the rest, that'll go through, and the rest of your code will flow nicely along. If your branches are unpredictable, you generally have a problem. So what you really want to try and avoid with packet processing is having an unpredictable branch per packet. And that's where you might need to get into techniques of dealing with branch-free code, like you'll see in some of our pipelines, in some of the code inside DPDK. Of course, the first time a branch is encountered, the branch predictor doesn't really know anything about it. It'll use some default rules, generally will take the branch, but that's only the first couple of times to take it. Thereafter, the branch predictor, it learns. The branch predictors get smarter, get better all the time. So if your branch is predictable, in general, you don't need to worry.
So, interestingly enough, right, every time the branch is encountered for the first time, it's always going to be a guess. Now, whenever the branch predictor gets flushed, it's always going to be a guess. Anybody write compilers for at any time? Any of you? Everyone. What do we call that guess in a branch predictor? It's called a static heuristic. It basically says, do this no matter what happens. If I don't get in the branch, if the branch predictor is missing, I will do a static guess. And the guess has two basic rules. And that is the interesting thing. And there are a lot of rules with that particular guess. So the first time I encounter a branch, it's a conditional. It's going along the code, it's a conditional jump. What's the processor going to do? It's going to guess. Should I take it, shouldn't I take it? It's a 50-50 shot, right? All the time. How you write code in that 50-50 shot determines whether you're off 15 cycles, 20 cycles, 40 cycles. So, by the way, so you realize why branch prediction at that first stage is this big a deal? It's because if you take an Intel processor, it fetches a certain set of instructions per second. It reads from cache or memory, it reads a block of bytes, it decodes a block of bytes, and that block number happens to be 16. So it reads 16 bytes and says, what do I need to do for these 16 bytes? And one of them is a branch, so it's going to guess. It's going to guess yes or no. Two important things about that, right? If you guess and you guess wrong, you're going to load another 16 bytes somewhere else. And that loading another 16 bytes maybe not in cache. The other interesting part is you loaded 16 bytes, if the first thing happens to be a branch, you guessed wrong, you may throw away the next 12 odd bytes, next few instructions. This is your first limiter to actually trying to scale code. Now we will eventually widen the pipe, make it bigger, but ultimately, how well you guide the compiler to that first guess is a big deal.
So there are a couple of things just to keep in mind then when you're writing code based on this, and a couple of them are here on the slide. First is the likely unlikely. Now don't use it everywhere. If the CPU branch predictor is going to be able to know which way your branch is going to go at runtime, let it do the job. Put this only on error conditions where you say this is extremely, incredibly rare, but don't try and put it on ones where you think, yeah, it's mostly going to be IPv4 traffic coming in, because it might not be, and you're better to let the runtime branch predictor do it because it's good at it, that's its job, it's good at it. So don't overuse those, but also use them on things like error legs, it's a good place to use them. But let your branch predictor do its work. And the second thing then is inlining. Because whenever you inline, now there's downsides to that and we'll touch a bit more on inlining later, but whenever you inline, if you've got a branch in that function, that branch then appears as multiple branches in the code, and as it appears to the CPU as multiple branches, they can be independently predicted. So that your function, whenever called from location A, always goes one way, but when called from location B, always goes the other. By inlining, it makes the job of the branch predictor that little bit easier.
Right. So another interesting point. We always think about branches as jump and compares and jumps. But there is one other critical branch, absolutely critical one. indirect calls, which we can predict. But there's a return call. So in other words, if I have a small function, and for I equal to something, and I create a function out of it, don't inline it, the last instruction in that is a jump, is a return. It's actually a branch sometimes that can't be predicted because you have a for loop in front of it that has something, or you have an if condition in front of it that has something. You now have a branch that's essentially unpredictable because of the return in it. That is an absolute disaster. Because what happens there is that will cause a machine clear pretty much. When you hit that return instruction, it returns, it speculates wrong, you've got a big problem. Small functions are a massive, massive problem. The smaller the function, the smaller the number of branches within a compact area is an issue. So compilers try to do a lot of stuff around it, but you can actually help the compiler by not doing some of these small things and making them inlineable completely, even if they are in different places. So what does inline give you? Inline gives you more context for a branch. That's the biggest advantage of inline. That is, all branch predictors are based on IP, the instruction pointer and context around the instruction pointer. An inline function in two different functions gives you two different contexts. Yes, it uses up more branch prediction entries, but it also gives you two different contexts to deal with. So code A and code B that deal with a common function will have branch prediction collisions between those two. Code A and code B with two inline functions will have a better probability for the branch predictor being tuned to both those functions. So, interestingly enough, we do a lot of this, and we actually do a little more inline than we should, to a large extent. There are some functions we should inline, some we shouldn't. But by and large, small functions, you should inline. Now, there is a whole section on that optimization guide that talks about this. There are compiler rules that talk about what you should do, what you should do. The one rule that everybody misses is never put two branches in a 16-byte window. If you put two branches too close to each other, you have insufficient context to go allow the branch predictor to do its job. Very critical thing, but if you look at the way it manifests itself inside C code, you put two if conditions right at the bottom of the C code with a return, or you put a if condition that has a 50% predictability with a return next to it, you've got a speculative branch that will die most of the time. That's how it works out. And you can actually write code and test it out. This will, if you present a 50-50 branch with a return, you have a problem. If you present two 50-50 branches, a simple probability, it will go down. So write your code in a way that avoids this kind of stuff. Simple as that. Now, here's another interesting thing. When you have a function that gets called, and then a branch as the first part of that function, that's another speculative problem, because it's usually within 16 bytes. And there you have another problem as well. So these are the kinds of things that you've got to watch out for. Standard coding practices don't talk about this. This is what compiler writers actually go and try to go figure out most of the time. So, talked about context. The biggest thing that, this is an interesting one. One of the interesting things about the Intel branch predictor is we do a lot of loop iteration checks. In other words, we can predict the number of iterations of a loop, but the number is pegged at 16. Okay, so we maintain context enough to predict loops of less than 16 very, very well. So if we look at the vector driver, it's an interesting story, because when we wrote the vector driver, I kept telling people, I wrote the base prototype for the driver and said, do this. And in it, it had, for I equal to 1 to 16, process 2 packets at a time. That's what the vector driver today does. So there's a very smart engineer in PRC that said, okay. Why did you do that? He changed it to 32, performance fell down. Changed it to 64, performance fell down. Now this is bulk, right? The more bulk you do, the better performance there is. Not really, not in this case. So what happens with this thing is that when you put it less than 16, we're able to predict well. If you put more than 16, it won't be able to predict well. By the way, this is documented in that optimization reference guide as a hint to a compiler writer saying, do this. So if you write code, keep it at smaller bursts sometimes will work better. Unrolling a loop in the inner loop inside a smaller burst works better. Okay. So those of us that write code like this for ages, okay, also sometimes known as the ancient ones because we used to write code at a time when processors weren't quite as powerful. This is what we learned to do. And the same things apply.
Okay, well, next one to watch out for, we're going to have to be, I think, a bit briefer on each of these so we use up all our time.
Oh, we will get brief as the...
Yeah. It would be to avoid sharing cache lines. So, I'm sure, again, this is one that most people are already aware of, but it doesn't hurt to restate it because we see it coming up again and again, and unfortunately it's also not entirely possible to always avoid this. But in general, whenever you've got a piece of data, and you're using it, it gets loaded into CPU cache. Okay? You got your L1, L2, L3 cache on most of our cores. Okay? That L3 is your sharing point. So anytime that you have a piece of data in one of your caches and one of your CPUs, and another piece of data on the same cache line, or the same piece of data that needs to be used by a different core, that has to come out of your L1 or L2 cache in your remote core, down to L3, and then back up the other side into the other core. And this takes surprisingly large amounts of cycles. Okay? It is in cache, and you are getting a cache hit, but it's not in the cache of the right core. So you end up with paying a penalty for that, especially if the data is modified. Okay? Because then it definitely has to be written back. The copy in your L3, your common cache is no longer clean. And so you end up paying a performance penalty due to this cache line going back and forward, being ping-ponged from one core to another. Okay? So, and if it's NUMA, it's even worse.
Where's the NUMA?
NUMA is so bad, we're not even going to talk about it. Okay? You definitely do not want your cache lines ping-ponging between NUMA nodes. Okay? But it's just within a node that this is a problem. So,
simple enough. So if you do L1 access is 4 cycles. I can get a 32-byte two 32-byte loads, one 32-byte store every cycle. And the latency is 4 cycles. It's pretty much hidden as part of the pipeline. Sandy Bridge was in a 2x16 load store. Haswell got better. Haswell got better. Skylake got better. L2 bandwidth is still 64-byte loads per cycle. So you can do one 64-byte load from LLC to L2 per cycle. On L3, which is LLC, on Skylake and Sandy Bridge and Ivy Bridge, you can do 32 bytes per cycle. And on Haswell, it's varied. It can go up to 32. And it depends on the core and on-core clock frequency. That's why it's kind of cashed out. Now, if you look at L3 access timings are between 30 and 40 cycles for the 4. By the way, these numbers for the 4-core desktop parts. The server parts have slightly longer access. For example, Haswell server parts is about 40 for the LLC because it's got more cores that has to go across. But the average is about 40. Now, the interesting thing that Bruce mentioned was when you look at a hit in a remote L1 or L2, and this is a hit, it's a shared line, not a dirty line, it's a shared line. The access time increases from 31 cycles for a 4-core part to 43 cycles for a 4-core part.
And my reaction on saying that was, whoa, that's really low.
But you have it as modified.
It goes up.
It
and
goes
the
up to
server
60.
parts are slower for these accesses.
Yeah. So now, imagine this. If we have a bigger number of cores, that number is going to likely get worse.
Yeah.
Why? Because you have more hops to get to. Again, this is network. It's a network inside a chip. More hops, more latency. More distance, more latency. It's going to increase. The more cores, it's going to increase. So what you do today to go fix some of these things that have smaller effects will have bigger effects in the future. You've got to be very careful about what you share, how you share it. Now, mind you, memory is still on an Intel CPU at 2 gigahertz, it's 140 cycles away. So it's quite significantly better today for modified lines. But you've got to start looking at these as being your worst case, right? So what happens when you hit an instruction that says move something into a register that's sitting on a different cache line, somebody else's L1? Well, you issue a snoop, the snoop goes across, somebody says, hey, I've got the data, modified it, stall, till I write the data back. That's basically the fundamental thing that happens, it stalls. So the moment you hit the instruction, you will stall, and you will stall for this kind of time. One thing on most CPUs is Intel is an out-of-order execution engine for a CPU. We will try to speculate as far ahead as possible. There are limits to what you can speculate on, limits to how far ahead you can execute. But we have to retire instructions in exactly the sequence that they were issued in. So the window of what you can do with stalls like this is quite limited. If I have a 60 cycle stall on a processor that can execute with that many ports on a single shot, you've got a pretty significant amount of stall time. So the obvious question is, if you stall, what do you do? Well, you have to do something, right? So the structure we work out is, and this is one of the reasons we do bulk. Any processor is going to stall. It doesn't matter what processor you talk about. ARM is going to do the same thing. Everybody complains about bulk, but bulk helps you get around that 60 cycle stall. You either do nothing for 60 cycles or you do something else for 60 cycles. Figure out what else you can do for 60 cycles. And what we do is we pull 4 packets, we issue 4 prefetches just to get around even this number, let alone this number. That's why we do a lot of this stuff. Yeah.
So we've always had a big internal debate over whether we've always had an internal debate over whether or not hyperthreading is good or bad.
Yep.
But a lot of times in this context, at some point you have to stall for something, and you might as well use those cycles for something else, which is.
So hyperthreading is good.
Okay.
Okay. Hyperthreading has a detrimental effect if you know how to handle it. It's actually fantastic. So hyperthreading splits your entire pipeline into 2. It splits your instruction into 2. So it still fetches 16 instructions, 16 bytes, but it decodes every other byte. So in other words, I will fetch 16, decode it for core 0. I will fetch 16, decode it for core 1. And then ping pong, ping pong, ping pong. So depending on how many instructions out of that decode you get valid into the rest of the pipeline, you could get 0, 1, 2, 3, or 4. How many you get valid determines how effective your hyperthreading will end up being for the front end. So if you have a very, very branchy bunch of code that keeps jumping around all over the place, the branch predictor is going to miss on, you're going to get nothing out of the front end. And that will cause an impact on hyperthreading. Because your CPU cores on the back end execution, the goal is to keep seven ports busy. So those 7 ports, if you guys can read this, there are 4 arithmetic units. Right? We can issue 4 add, XOR, move, sub, whatever, arithmetic functions, 4 per clock cycle. Okay. That's the objective. The objective is to keep those busy. If you can't keep those busy, you've lost cycles. Now, keeping busy happens to be a bunch of stuff we do at the front end, which is why branch prediction is so important. If you do it right, you can get more instructions into the back end of the pipe. And by the way, the way to read instruction cycles, right? We have in the optimization guide, there's this latency and throughput chart. Looks like gobbledygook to most people, but it tells you how fast instructions flow through the system. So if I have an instruction with a latency of 1, it essentially means there's only 1 micro-op for that instruction most of the time, which essentially can be executed on n number of ports. So if you see 1 0.25, it means essentially I can execute that instruction on 1 of 4 execution ports in 1 clock. And it's a very easy way of looking at this. But that's what we're trying to keep busy. So hyperthreading typically gives you about 30%. It can give you much higher numbers if you've got a lot of memory stalls. And if you get the instruction mix right.
Yeah, you're stalling on PCI access for the.
Right? So a lot of what we've done is try to get away from stalling on PCI to get to L3 is your base point. But again, even L3 is still 60 cycles away. You could stall a CPU for 60 cycles. You could be executing 240 instructions in those 60 cycles. Think of it from that standpoint.
And the thing to remember is that those other instructions you execute can't be dependent on the one that you're stalled on.
Yes.
So that's the other reason to do batching and burst routines for this, to pull multiple packets at a time, because if you're stalled waiting for packet A, packet B, C, and D are generally not dependent upon that because you're operating on completely different data. So it's just another thing to keep in mind whenever you're putting these together. If you've got a memory read, that's going to be hitting L3 cache, hitting the remote cache. It's going to take some time, going to be a stall. You maybe want to try and make sure there's other instructions around it that are not using the same data as that, because then they can pass it out in the pipeline. They're not dependent on the result of that operation, and the CPU can keep on chugging away.
Right. So one other question. You guys have looked at DPDK performance, right? Has anybody actually looked at what the IPC of the code that runs actually is? When you take L3 forward, you take the test PMD packet in, packet out schemes. What is the IPC of the code we typically run? Any guesses? Instructions retired per clock. Who said that? 2.16. That's just two things. Competitive guy. Okay. No, but interestingly enough, it's actually low. It's 2.4. 2.4 means I've got essentially 2 execution units operating most of the time out of 8. Is there room to grow? Yes, that's what we look at.
But again, back to the locality in forwarding is, look at the number of load stores you've got.
Now, so interestingly enough, right? I mean, you can do the same thing on a TCP stack, and we know that the TCP stack gets actually worse. It's a question of not optimizing where you want to go. So we could optimize the TCP stack and get a lot of performance out of it. We know how to do this. It's a question of what do you need, what functions do you need in networking that we can actually speed up. And then once we speed it up, what can you do with it? That's the objective of what we look at. Optimization is not for just optimization's sake. You can do a lot more with it. Right? So to put it in perspective, if I increase performance on a complete path, that they pack it in, do a bunch of lookups, fib route, rewrite, encapsulate a node, and I increase it 2x, the end goal is you reduce your core consumption by 2x. You reduce your cost by a pretty big factor. That's what the optimization is for. Yep.
Yeah, but I gave you a number of 2, but that was for code that I see is usually closer to 0.6.
Yes. Yes. So there's lots of room to grow.
That's what you're saying.
So you can, there are two philosophies, right? You can throw hardware at the problem and say, look, I will try to do all of this stuff offloaded. Fixed software is cheaper, you can actually do it. 0.6 to 2 will give you a 2.5x jump in performance, a 2.5x cost reduction in your BOM cost on your board, if you do it right. That's what we look at. So, of course, with everything, it's easy to do stuff incorrectly. So, you want to do this?
No, work
So
away.
there's an interesting
You're
one.
full flow. I won't interrupt.
Prefetching. It's easy to do stuff wrong.
It's very hard to get right.
It's very hard to get right. Most people don't understand why it's hard to get right. We issue a software prefetch. We think it comes back in certain cycles. It doesn't come back in certain cycles. You still see the same problem. See, the problem really is, by the way, so back in computer science, there's a class called algorithms and data structures, and all of us snooze through that one. I don't see anybody that has actually sat through one of those and paid attention to what data structures were. But that's what this is about. So what happens with a prefetcher is there are 2 types of prefetchers: a software prefetch that you issue, you control, and there's a hardware prefetcher that runs ahead of you. And quite often it runs in the wrong direction. Okay? Networking by definition is unpredictable as to where the packet lands and how it lands. So it will run ahead and it will try to predict what you're trying to do and fetch. And quite often it gets it wrong. Is there anything as a completely predictable networking prefetch? No. But that extra prefetch does 2 things. It adds overhead. Remember, you can load 64 bytes into LLC every cycle. You can load 32 bytes. It's using up that bandwidth. If you get it wrong, it's using up that bandwidth. If you make a mistake on a prefetcher, and the prefetcher can make mistakes, it will prefetch and get you into a cache line sharing problem that you didn't anticipate. Think about that part.
Yeah. One example of that we have in the code is the packet distributor. Whenever we were working on that, we had one nice cache line that's going to be shared by each core. So you had the distributor core and the other worker cores, and you passed the cache line back and forth. Read its cache line. The hardware prefetcher then was looking at the adjacent cache line and pulling it in as well because it anticipated it was going to use it. The only trouble was that cache line was actually meant for core B. So we actually had to stick some extra cache lines in the middle so that it didn't matter what the hardware prefetchers thought we were going to do, it was just unused space anyway. And it actually made a performance increase because of this.
So even better. So that's an interesting question. Interestingly enough.
Prime number?
No, don't do it by cache lines. So the interesting bit is this. See, if you look at code that's going to be written over a few years, okay, and I've been doing this for a while, the interesting bit is these things will try to get smarter. The hardware prefetchers will try to get smarter. They'll try to predict more aggressively and better. Like branch predictors, we have a pretty good 70-80% branch prediction rate on most things. We will not see too many branch misses on Intel CPUs. We do them even reasonably right. Okay. This prefetcher will do the same thing. We started with, essentially in the old Pentium days, a next cache line prefetcher. 64 bytes, we fetch the next cache line. Later people just said, okay, they keep going sequentially in the pack. Works for TCP stacks. I want to process sequential stuff. And then somewhere along the line, we started seeing code that was jumping around. But they were jumping in essentially strides. I access something 64 bytes, then I access something 128 bytes beyond that point, then I access something else. These were all the skip algorithms that showed up. Lots of skip algorithms. So what ended up happening there was we started putting a stride prefetcher in that says it tries to predict your next fetch by looking at strides. And then what we found was there was always a locality thing that used to happen with bad code. Code that was written that said that was branched across two different cache lines. Cache line A, cache line B. And what happened with split cache line loads was we could prefetch the first one, but the second one used to hang around 4 bytes in the next cache line. So then came a spatial prefetcher that said, look, pick the paired cache line. So fetch line 0, fetch line 1. And if somebody accesses line 3, fetch line 2. So now all of a sudden it became 128 bytes. So the potential for damage keeps increasing, right? So if I have a packed data structure, 64 bytes for flow A, 64 bytes for flow B is going to get fetched by somebody that fetches flow A, and flow A is going to get fetched by somebody that fetches flow B. Okay, keep them apart. Put them 128 bytes apart. Predictor will figure it out. Put a prime number apart. It will figure it out at some point.
19.
Easier methodology.
Depends on how much memory you want to waste, right? To be sure.
Much easier methodology.
Yeah,
A couple.
Don't care about it.
Yeah.
If it's not,
But very easy methodology is one level of indirection. Put a bunch of pointers that will point to data structures, but those data structures essentially are distributed. So you really can't get a prediction methodology out of it. So what you get is access. The branch predictor says there's not much. Okay. And off you go. So all of a sudden you don't have this collateral damage that, by the way, could cost you 60 cycles today and then a few more cycles tomorrow, right? That's the intention. So now all this stuff is going to be present on every processor you work on. It's not going to be on just IA CPUs. IA CPUs just happen to be a bit further ahead right now, but it is going to be there on most of these. Okay. Yeah.
This problem is actually worse on the DRAM. So using random for particularly repeating arrays, if you don't use random offsets,
Yes.
you will absolutely, by orders of magnitude, stretch your delay with DRAM.
So DRAM has got another peculiar thing. In DRAM, you always read 64 bytes on a standard line. And if you start prefetching aggressively to DRAM, there are two side effects. One is, latency. Second, most people don't think about is power. Now this is another religious debate. Okay, so once upon a time, about 6 years ago, a couple of hardcore Linux types showed up in Oregon in my lab, and we were talking about net IP alignment. Okay, and they were saying, net IP alignment is great, so on and so forth. I said, look, that's a religious argument. I don't want to enter a religious argument. I'll show you the impact of net IP alignment on a power budget. So you run today, if you look at an IA CPU complex, it's got 8 DIMMs sitting next to it. Each of those DIMMs could burn 15 to 20 watts of power at peak bandwidth. If I took something that is running X gigabits per second through memory, and I doubled it, what do you think the power burn on memory is? That's what net IP aligned to memory does. It accesses 2 memory lines where 1 should be sufficient. Simple as that. Now, if you contain it all within the processor and you don't burn power, it's fine. But most stuff goes to memory. If it goes to memory, you're burning more power. The difference between what you burn is 2x the memory bandwidth. Read, modify, write, 2x the memory bandwidth. These are the things you try to actually go avoid, right? So prefetching is a issue. You've got to think about this from just more than one perspective. It's not just about what you prefetch and how you hide latency. It's also about how much less damage you can cause to other data structures that are going to get prefetched at the same time. Okay. So back in school, one of our data structures thing was, hey, pack everything. That's the traditional way of doing things. Pack everything. Packing everything is not necessarily a good thing for performance, especially as we start looking at higher and higher and higher line rates. Okay? So just to put it in perspective, right? You guys are all in networking. 70 nanoseconds in 10 gigabit terms was just slightly higher than a single packet at 64 byte arrival. Min packet arrival is 67.2 nanoseconds. 100 gigabit, 6.72 nanoseconds. 1 miss to memory and you're down 10 packets. You're 10 packets behind on small packets. Okay. That's how critical it starts to get. We normalize around 128 byte packets. 5 packets behind if you miss to memory. And you don't hide that thing. Because you're essentially stalling. Nothing else you're doing. It's not going to add latency. You're simply stalling anyway. So, prefetch it. Next one.
Sure. Next thing to consider is, again, something people are really familiar with, is working in bursts. Or more accurately, what you want to avoid doing is doing things per packet. Now, we've already touched on this already in terms of fetching in bursts to hide your latency of a stall reading memory, reading L3 cache, reading a remote cache line, things like that. But it's also the smaller stuff that needs to be considered as well. Function calls. The function call overhead, when done per packet, starts becoming significant. Whenever you have your compiled code, if you ever look at the assembly output, which unfortunately I've recently had the necessity to do when trying to track down a bug that only occurred in certain compiler versions, you'll see you got before your function call a couple of moves to save away the registers that are going to be clobbered, that are for the function to actually use itself. Then you got the call, and then as soon as it gets inside the function, you got your push of your RBP, then you move your stack pointer to RBP, then you got a whole bunch more push calls, and that's just all pure overhead. So you can be burning 10, a dozen or more cycles just by making a function call. Now, if you've got that dozen cycles, say, and you're doing that once every 16 or 32 packets, well, you do the math, it's less than half a cycle per packet. But you do that for every single packet, it starts to have a noticeable effect on your pipeline. But then there's also the bigger stuff too. If you've got a read or a write to something on a PCI bus, well, that's huge, huge operation. So you absolutely have to do that with a big burst. So you really are looking at burst of 32, which is why we do what we do in the vector drivers and in the non-vector drivers in DPDK, to hide that MMIO operation, amortize the cost of it. Atomics, again, I'm sure most people are aware that that's very expensive. You definitely don't want to be doing one atomic operation per packet, do it per burst. Ring NQ-DQ. This is a nice one because we have the unit tests in DPDK to go and measure that. So you run your ring performance auto test, and you see within a core, within 2 hyperthreads, going across cores, going across numinodes even if you're really curious, you just run it, and it'll tell you it takes X number of cycles per packet when doing 1 at a time, when doing 8 at a time, or when doing 32 at a time. And it quite clearly just shows you the benefit you get from amortizing these costs across bursts. So remember the big stuff, but also don't forget the small stuff, which is why we inline what we do. And as a final thing for me on this is whenever we're looking at using external memory, external mempool, external memory management, it's something we're considering and thinking about right now. It's the reason why we have our existing mempool caches and our mempool put and gets inlined, to avoid that overhead whenever you're going to put one buffer or pull one buffer. We want to make sure that pull from the cache from that per core cache, which is a stack operation. You basically read a value and decrement a pointer, or write a single value and increment a pointer. Very, very small. So you want that still to be inlined. So this is why we're looking, if you want to have an external memory manager for managing the buffers, maybe in some hardware or using a different scheme other than the shared ring we have, why we're saying, well, let's put the actual indirection, the function pointer, at that second stage. So we reuse the caches as is, so that you can keep the really efficient single packet operations. And then whenever you want to work out a big burst, whenever you need to flush it back to your external storage, be it a ring, a stack, a hardware block, then you've got your function pointer call. But again, it's amortized over your 32, 64, even 256 packets, depending on your mempool cache size. So that's just something that we're looking at.
No, so simple enough, right? People say locks are bad. Locks aren't bad. It's how you use locks that can be bad. If I have a lock and I push 32 packets within that lock, you just amortize the cost. It takes about 60 cycles to do an uncontested lock unlock. 32 cycles is 2 cycles per packet. You do them once every packet, disaster. So there's actually no bad thing. All the mistakes are essentially behind the keyboard, 99% of the time. Yes?
I was going to raise one issue that showed up both in the DPDK and in Linux. Is one surprisingly expensive operation is returning the buffers after transmit complete. And
Yes.
right now, even in the DPDK, we don't have a bulk function. We don't have drivers using the bulk function.
Well, we try to, but
So actually, we should do better than what we have. Now, interestingly enough, right? And this is the Intel data-driven philosophy, right? It hasn't shown up as a big hotspot yet. It's beginning to show up as one now. But the base, there are two problems with that entire return sequence, right? One is there's no bulk. But the second one is that essentially that entire thing happens so late, it is always a cache miss.
Right.
Okay? And that second one is actually costing us cycles, right? It's costing us a stall. But the thing is, it's amortized across 32 or 64 or 128 packets, then it's not showing up as a big deal. But it is a stall. It's a stall that you could do a lot more cycles in. That's something I've been trying to figure out what to do with. We took one small stab at the bulk side,
yeah.
but I think we could do.
The big complication there is that whenever you're freeing after TX, you can't write in a general driver any assumption about where those buffers came from.
Yes.
So you have to actually go and look at each buffer, say, right, what pool did you come from?
They're all the same, yeah. The 99% of the time they're all the same pool.
99%, but is that 1% that is killing us?
Yes.
So,
but by the way, so the interesting
yeah.
bit is, again, we look at hot path in a code, 99%. One of the things I use T-Rex for is to look at that other 1%, because that other 1% actually has a bigger impact on this 99% than we think. So a simple example, I think this was there in the OVS code, right? Every time OVS drops a packet, it increments an atomic. Every time, okay? Now, exception part of the code, right? Most people don't think about this happening all the time. But what happens if you're back pressure and you're going to keep dropping packets again and again and again? Disaster. That's the thing. So programming for the success case is great. Programming for the error cases, you've got to look at. And that's where we seem to lose a lot more cycles sometimes than in the actual success cases. So to Steve's point, right? If I get into a back pressure situation and I keep returning that TX becomes my critical path, I just died. The second part of it is we had the same functions operate for receive and transmit. The receive side, okay, so L3 forwarding, when it actually picks up a packet, and the microcosm for us is very small, so we can actually analyze it well, right? So it picks up a packet, it can't transmit. When it can't transmit, it returns them, and that was a for I equal to 1 to whatever, put one back, put one back, put one back, put one back. We really didn't expect it to get hit most of the time. But it so happens since Niantic essentially is transmit limited, and most NICs are transmit limited, they're not receive limited. They will back pressure 20, 25, 30% of the time. In other words, 25% of the time you're executing for I equal to 1 to n, no loop iteration possibility, no branch prediction possibility, single packets at a time, and no atomic increment every time this happens. This is what, by the way, this is what our analysis of our own code is. If we make the mistakes, I'm pretty sure everybody makes them.
By the way, the same problem for the ring. If you read faster and the writer, you have this.
Yeah. So the other thing everybody doesn't think about, right? If I have 16 rings to
for
pull,
sharing.
if I just look at 16 rings to pull, everybody looks at the case that has all those 16 rings full and everything flies. What about if 2 rings were empty? Okay, think about those. It's those exceptions that cost you. Hey.
We find some but the technical issues when you have the queues. There's so many queues, there's so many going to be mapping that we have questions.
Correct.
So the ultimate limitation is get optimized when because there are queues, then sometimes there are thin betas,
Mm-hmm.
Yes.
Yes. So
when we get deep queues, it's getting worse.
yes.
So sometimes we basically compromise, lose packets, drop packets, and get logs for the ultimate.
Exactly. I mean, see, so that's the other interesting bit, right? Don't, and my reason for saying something about locks was very simple. Don't look at locks as bad, won't do. There are certain cases where it actually will be better.
For the reader, right?
Yeah.
Yeah.
Yes. And you can use them effectively. I mean, there are certain places where if you did have some of these signals, if you restructure the code in a slightly different way, Vertio was a perfect example. You would actually end up faster than trying to put the most optimization techniques around something. So we're looking at this. This is what our thing is. And your impact, this is why we try to optimize stuff. It's these things, Vertio, etc., that cost us more than anything else.
The other thing that I always run into is I meet people, they always think a reader-writer lock is faster than a spin lock.
Oh no.
The reality is a reader-writer lock is much worse, even in the unintended case.
Yes.
And the only time you should ever use a reader-writer lock is if the reader is going to be holding, you're going to have multiple readers holding on to something for a significantly long time, which hopefully in DPDK-based code you would never have.
Yeah. And that's in terms of locks as well for everybody. Don't forget there's the new TSX extensions
Yes.
for your really high-end house walls and broad walls. Make locks slightly less of a problem.
So again,
if you can use it right, it can give you some really nice benefits, really nice scalability in your locking.
Yeah, so interestingly, there's lots of these kinds of things you could do, but don't look at, just because something was done and something says, this is traditional holy grail incorrect, don't. Yeah. So Vincent, that's what you should look at. You should look at both DDIO as well as CPU cache allocation, because in Haswell-Broadwell you can actually allocate CPU cache, so that you can constrain what is critical to not evade, and then you've got your balance that you need.
Don't you think we should make it as another EM, whatever, as a DPDK? Something that
Yeah. So we are actually that is something we are looking at, right? The entire QoS stuff as part of DPDK. I think we have to push some patches for that particular thing. It would be good because even if systems are not enabled, older kernels, whatever, we will have them.
So the next item we had for our 7 deadly sins, I came up with the title, by the way, was incorrect inlining, and I think we've probably touched a lot on inlining already, so I'm not sure how much more we really have to say here, but it really does come down to a trade-off. Okay, we've talked a lot about the benefits of inlining. Okay, eliminating our parameter passing overhead, increasing optimization opportunities for the compiler, better branch prediction. Okay, however, the downsides are. Okay, that's Venky, not me. Good. Downsides are obviously you get less flexibility. Your function is no longer part of the ABI. It's actually embedded in every application that uses it. It often means that, say, your data structures now have to become public, and you can't move things about inside your private data structures, even though they may be internal, because you've got, let's say, your hash lookup function is inline. Well, any fields that it uses now become part of that public ABI. So there really is a downside in that way to inlining. So it's not, unfortunately, a panacea, which is why Stephen is always hammering us about, you're inlining too much, and maybe indeed we are. But going back to other things we talked about, things like per packet overhead and using bursts, for me anyway, I think is a good rule of thumb. Anything you're doing per packet, you probably want to avoid your per packet overhead by inlining it if it's in any way a smaller function. Whereas if it's working on a burst of 32 packets, then probably the additional flexibility you get from having it in a C file, part of the ABI versioning, being able to keep your structures private and things like that, probably means that you want to make it a separate function and not do the inlining, because any function overhead is going to be amortized over the cost of those 32 packets.
Right.
Thank you. You got anything
But
else?
one interesting thing, and there's always the yin and yang thing with everything,
Yeah.
right? If you don't inline certain functions that are extremely often called, so as an example, if I have a spin lock function that's called by 4 callers, this is the case in Linux, by the way. Linux has this problem. It has a common pthread library. Pthread library implements a spin lock, mutex. And it's a common function, works well. Except it has no context now of caller A, caller B, caller C, caller D. If there are 500 callers, it's got a problem in predicting. In this case, it would be faster to inline that entire pthread function than it is to actually call it individually. Now, what happened with the individual part of it is, if you look at the Linux code, we put in code to figure out where the caller is coming from and then try to predict on that baseline whether to do hardware lock elision or not do hardware lock elision because of the granularity of the calls. This is a real case. If you did this as an inline function, they would get their own BTB, they would get their own prediction. It would simply work.
And also the other one is a lot of times you have inline functions where people call it with a constant parameter. The compiler can go, okay,
Yes.
well, this
Yeah.
will never be true. And
Correct.
go away.
Yeah,
Yeah,
The classic one is you have a hash function that has an unrolled loop.
correct.
yeah.
Somebody calls it with an IP6 address.
Yeah, or we also use that in the rings code as well for our difference between our bulk function and our burst function was implemented in that way as well with a constant last parameter to avoid code duplication.
That took a lot of work to get right across all compilers.
Okay.
I was going to ask.
I thought it worked pretty much first time.
Yeah, okay, so-
Mostly. Anyway, that's another thing, yes, you can do with inlining, but that's more, can often be used just internally within a C file without making it, again, part of that public API. It's really the public API, ABI, that I would be concerned about due to the overuse of inlining. It really ties your hands in terms of your data structures.
So the interesting bit is this, right? About when we started this about 6 years ago, 7 years ago with DPDK, we chose to be very conservative about everything. Everything that could yield performance, we bias towards. In other words, excessive inline. We bias towards excessive bulk. We bias towards completely lock-free stuff. It's not necessarily bad. Some of these things, you could do traditional things the right way and still get away with a lot of performance. Just have to know how to do them at what time, right? And that's, by the way, the collective thing that we've got to figure out how to work is do the right thing so that we get the knowledge out that this is what happens if you go off the rails.
Well, that's why you always find it sits.
Yes.
Code load, you get cache resist. That's hidden.
Hidden.
And you do it all.
Yes.
If it's on 101, that becomes very bad.
And so if you really think about it, right, this networking industry and the APIs that exist in the networking industry haven't changed for ages. TCP protocol, TCP IP stack still process 1 packet at a time. In the age of 100 gig, it's not something that will sustain.
No, I think we've got a couple more points for you, David.
Which is, how smart is GCC when you turn on link time optimization?
Oh, very smart. So you got to do 2 things on GCC, okay? And I think a lot of us don't trust compiler tools, but GCC has actually gotten very, very sophisticated, very smart. The 2 things I look at all the time are, if I turn on PGO, profile guided optimization, in other words, it runs, it figures out what goes on, and then tries to suggest changes in code. Quite often that actually helps. If you can put the right stimulus to it, in other words, test all the exception conditions, it will give you a pretty good hint of what to do. It's a start point. It's a better start point than trying to figure it out yourself. Use that. Okay. But GCC's gotten, link time optimizations have gotten very smart. They're getting better and better and better. So I think it's, we should look at seriously looking at taking some apps, profiling it, see what it does, going after it.
The problem is the link time.
Okay.
It blows your link time.
It blows your link time. But I think it's a smaller price to pay. If you can arrange it so that you know the input stimulus correctly. By the way, just FYI, he works T-Rex, okay? It's an interesting It's a very interesting tool from the sense of looking at all these kinds of conditions. Rather than 64-byte packets, looking at the exceptions that happen in the system, right? And that, once you start looking at that as a science, it actually works well.
You mentioned the use of things like registers and different the compilers that we treat indexed arrays and pointers very differently. Right?
Yes.
They tend to perform significantly better using indexed arrays than pointers.
Actually, used to be the case. Used to be the case. It's gotten smaller and smaller. It's particularly true on ARM, where you don't have an index mechanism in the instruction set. IA has it, so it's not been that big a problem in IA, or actually no, it was virtually in PowerShell. But it's there on some things, yes. But I think compilers have gotten better around using that. But if you did define it completely incorrectly, it's going to give you a problem. And no amount of compiler smarts will work on badly structured stuff.
Remember about 6 months ago I said I was seeing worse performance when running as a shared library versus not.
Right.
The reason is when you're doing as a shared library, you can't get LTO of the shared library.
How?
That's when you static. So it
Actually,
turned
that's
out
a-
that was the actual cause.
That was the cause.
Yes.
So actually, that's an interesting one. See, shared library has another particular problem, right?
The code, the whole instruction, right?
Yep.
Yeah, but that was the observable effect was.
So one other thing to think about, right? Shared library means VDSO. VDSO also means essentially one per page. One per page also means TLB pressure. Right? That's another issue that we've got to actually at some point figure out how to address.
So we're getting to the end now of the last two. So again, hopefully they will get short and shorter of these because we're getting near the end of time as well. So bad data structures, again, this is all about memory usage, cache line usage. Make sure you get all your data that's going to be used for a single core on the one cache line, that you don't have data that's to be used on different cores mixed into the same cache line. In other words, sort your data properly into your appropriately colored bins.
And see the other interesting thing, right? So we talk about high performance Xeons, these make a bigger impact on the smaller processors. Badly aligned data structures on Atom, Quark, ARM will make a much bigger impact than it would on a Xeon.
And in DPDK, anybody who's looked at the code will obviously see we cache align all our data structures. It's just to help prevent any accidental overflow of one data structure onto another cache line shared with a completely unrelated data structure, and avoid this accidental false sharing, as it's called.
But partitioning and grouping and padding within the data structure is also very, very important. Like grouping, grouping objects that are going to be read and objects that are going to be written separately, and things like that.
No, so that's an interesting one, because when we look at ADI and a structure, we keep adding stuff to the structure. Not necessarily the right thing to do. We have to group stuff logically where it makes sense, but that's got another detrimental impact, right? So have to think about things in these ways. If you have cache lines that are purely read, they'll always be faster. 17 cycles, remember that part, between a read line and a read modified line. Right? So if you have a line that's going to be modified heavily and read by a few, versus pushing stuff into purely read lines, it's a big, big deal. People don't think about this when they add stuff to data structures. Okay. Now, by the way, the interesting part is we find out this after the fact. We just keep adding stuff and then run VTune, run this. Eventually, some stimulus will spit out this particular problem. So for us, it's a question of getting all the stimulus right for all the forwarding paths we have.
Yeah, actually, Venki, when I was at SGI, we used to document that. So there you go, DPDK. Just
see, that's called the ancient one, man. We used to do this once upon a time. We lost the art of doing this stuff somewhere, right? It has to come back, because this was what we did. We had to do it 100 megabits on a 386. How do you do it?
You say that the last one, there's one topic, I know we are running out of time, which is the Linux ABI, which push 64 bits stacks, 64-bit pointers with all the GPS from Intel, knowing there are some mods which are unused with Linux. That would be very nice to have the all 64-bit registers, but a 32-bit mods.
Yes.
So, I mean, have you made any
X32.
benchmarking? What's the performance gain would we have?
If you're a register
Because if
pressure,
we need some
sorry.
input to push the next people.
You've done it, right? X32. What's the performance better?
Last time we checked about 6 to 8%. 60 to 80%. 60%.
So why don't you show it on the DPDK units and we'll show
It's there.
It should be there.
It's there.
There, yeah,
Yes.
yeah, yeah. X86 was a 64_32, I think it's called.
Do we
Rather
still,
awkward
do
name.
we,
Constantine
do we
worked on
still
it.
have Chris Wright when he went from Red Hat in the rooms? I want them to hear that. Please do something with ABI. We have 60% improvement.
So anything that's register pressure gets 2x the number of registers. What?
I'm full with you on that. But the problem, if the day we do that, we are going to patch all the Linux distributions. Yeah, then we need that.
So we've done most of the work, right, at this point. We've done,
Yeah, I mean, the compiler, the Proccessing thing is there,
Yes.
there's an arch, it's everything.
Everything's there.
It's just a distro,
has to
needs
support it.
that to rebuild.
Yeah.
Even ICC's got it now.
Yeah, we were actually the last to get it, to be quite honest. I mean, we've been pushing this for a while, right? And Larry's been at the front end of this thing. He can tell you how, pretty much to a T what these numbers look like.
Yeah. I think we're pretty much done. That was the 6th, and we thought we'd add an easy one as the last one. Don't make system calls. Keep it easy. So, any more questions that haven't already been asked, and I'll let Venki answer them all.
No.
Otherwise, I think our time is done. Thank you.